Chapter 11. Temperature and Phases of Matter. On a hot day, a glass of iced tea develops water droplets on the outside. The water does not seep from inside the glass to the outside. So where does the water come from? It comes from the air. The cold glass causes water in the air, a gas, to condense into liquid water. You are seeing direct evidence that water exists in three phases: solid, ice, liquid, and gas. The phase that water takes depends on the temperature. Measuring temperature. There are two common temperature scales. On the Fahrenheit scale, water freezes at 32 degrees and boils at 212 degrees, figure 11.1. There are 180 Fahrenheit degrees between the freezing point and the boiling point of water. Temperature in the United States is commonly measured in Fahrenheit. 72 degrees Fahrenheit is a comfortable room temperature. The Celsius scale divides the interval between the freezing and boiling points of water into 100 degrees instead of 180. Water freezes at 0 and boils at 100 degrees C. Most scientists and engineers use Celsius because 0 and 100 are easier to read than 32 and 212. A weather report that says 21 degrees C in London, England, predicts a pleasant day, good for shorts and a t-shirt. A weather report predicting 21 degrees F in Minneapolis, Minnesota means a heavy winter coat, gloves, and a hat. Because the U.S. is one of the few countries that use the Fahrenheit scale, it is useful to know how to convert between Fahrenheit and Celsius. We can sense the cold, but not very accurately. A thermometer is an instrument that measures temperature. A type of thermometer you have likely seen uses colored liquid alcohol to sense temperature. As temperature increases, the alcohol expands and rises up a long, thin tube. You can tell the temperature by the height the alcohol rises. The tube is long and thin, so a small change in volume makes a large change in the height, figure 11.2. All thermometers are based on a physical property such as color or volume that changes with temperature. A thermistor is a device that changes its electrical resistance as the temperature changes. Some electronic thermometers sense temperature by measuring the resistance of a thermistor. There are some chemicals that change color at different temperatures. These are used for aquarium sticker thermometers that are placed on the outside of a fish tank. Imagine you had a microscope powerful enough to see individual atoms. You would see the atoms are in constant motion, even in a solid object. The atoms are not fixed in place, but act like they are connected by springs, 11.3. Each atom stays in the same average place, but constantly jiggles back and forth in all directions. As you might guess, the jiggling means motion, and motion means energy. The back and forth jiggling of atoms is caused by thermal energy, which is a kind of kinetic energy. Thermal energy is proportional to temperature. When the temperature goes up, the energy of motion increases. That means the atoms jiggle around more vigorously. The higher the temperature, the more thermal energy atoms have, and the faster they move around. Temperature measures a particular kind of kinetic energy. If you throw a rock, the rock gets more kinetic energy, but the temperature of the rock does not go up. How can temperature measure kinetic energy then? The answer is the difference between random and average. For a collection of mini atoms like a rock, the kinetic energy has two parts. The kinetic energy of the thrown rock comes from the average motion of the whole collection, the whole rock. This kinetic energy is not what temperature measures. Each atom in the rock is also jiggling back and forth independently of the other atoms in the rock. This jiggling motion is random. Random motion is motion that is scattered equally in all directions. On average, there are as many atoms moving one way as there are moving the opposite way. Temperature measures the kinetic energy in the random motion. Temperature is not affected by any kinetic energy associated with average motion. That is why throwing a rock does not make it hotter, figure 11.4. There is a limit to how cold matter can get. As the temperature is reduced, molecules move more and more slowly. When the temperature gets down to absolute zero, molecules have the lowest energy they can have, and the temperature cannot get any lower. You can think of absolute zero as the temperature where molecules are completely frozen with no motion. Technically, molecules never become absolutely motionless, but the kinetic energy is so small it might as well be zero. Absolute zero occurs at minus 273 degrees C or negative 459 degrees Fahrenheit. You cannot have a temperature lower than absolute zero. A temperature in Celsius measures only relative thermal energy relative to 0 Celsius. The Kelvin temperature scale is useful in science because it starts at absolute zero. A temperature in Kelvin measures the actual energy of atoms relative to zero energy. The Kelvin unit, K, of temperature is the same size as the Celsius degree. However, water freezes at 273 K and boils at 373 K. Most of the outer planets and moons have temperatures closer to absolute zero than to the freezing point of water. To convert from Celsius to Kelvin, you add 273 to the temperature in Celsius. For example, a temperature of 21 degrees C is equal to 294 degrees K, 21 plus 273. When absolute zero is the lower while absolute zero is the lower limit for temperature, there is no practical upper limit. Temperature can go up almost indefinitely. As the temperature increases, exotic forms of matter appear. For example, at 10,000 degrees C, atoms start to come apart and become a plasma. In a plasma, atoms are broken apart into separate positive ions and negative electrons. Plasma conducts electricity and is formed in lightning and inside stars. Phases of matter. Most matter around you is either solid, liquid, or gas. A solid holds its shape and does not flow. The molecules in a solid vibrate in place, but on average don't move far from their places. A liquid holds its volume, but does not hold its shape. It flows. The molecules in a liquid are about as close together as they are in a solid, but they have enough energy to change positions with their neighbors. Liquids flow because the molecules can move around. A gas flows like a liquid, but can also expand or contract to fill a container. A gas does not hold its volume. The molecules in a gas have enough energy to completely break away from each other and are much farther apart than molecules in a liquid or solid. When they are close together, molecules are attracted through intramolecular forces. These forces are not strong as the chemical bonds between atoms, but are strong enough to attract neighboring molecules to each other, figure 11.5. Intramolecular forces have different strengths in different elements and compounds. Iron is a solid at room temperature. Water is a liquid at room temperature. This tells you that the intramolecular forces between iron atoms are stronger than those between water molecules. Within all matter, there is a constant competition between temperature and intramolecular forces. The kinetic energy from temperature tends to push atoms and molecules apart. When temperature wins the competition, molecules fly apart and you have a gas. Intermolecular forces tend to bring molecules together. When intermolecular forces win the competition, molecules clump together tightly and you have a solid. Liquid is somewhere in the middle. Molecules in a liquid are not stuck firmly together, but they cannot escape and fly away. The melting point is the temperature at which a substance changes from a solid to a liquid, melting, or liquid to a solid, freezing. Different substances have different melting points because intermolecular forces vary. When these forces are strong, it takes more energy to separate molecules from each other. Water melts at 0 degrees. Iron melts at a much higher temperature, about 1500 degrees C. The difference in melting points tells us the forces between iron atoms are stronger than between water molecules. When enough energy is added, the intermolecular forces are completely pulled apart and liquid becomes a gas. The boiling point is the temperature at which a substance changes from a liquid to a gas, or from a gas to a liquid, condensation. When water boils, you can easily see the change within the liquid as bubbles of water, vapor, gas form and rise to the surface. The bubbles in boiling water are not air, they are water vapor. It takes energy to break the bonds created by intermolecular forces. This explains a peculiar thing that happens when you heat an ice cube. As you add heat energy, the temperature increases. Once it reaches 0 degrees C, the temperature stops increasing as the ice starts to melt and form liquid water, figure 11.6. As you add more heat energy, more ice becomes liquid, but the temperature stays the same. This is because the energy you are adding is being used to break the intermolecular forces and change solid into liquid. Once all the ice has become liquid, the temperature starts to rise again as more energy is added. The graph at the right shows the temperature change in an experiment. When heat energy is added or subtracted from matter, either the temperature change or the phase changes, but usually not both at the same time.